Welcome back to today's video. In today's video, I want to discuss how we can evaluate our model using cross-validation as opposed to validating our model using our training set. Before I get into today's video, make sure you hit the subscribe button down below and like the video for more content just like this. Let's get right into it. All right, so let's discuss here what we did in the last lesson. In the last lesson, we discussed the decision tree regressor. Remember, the decision tree regressor supported nonlinear relationships, and we determined that it might be better than the linear regressor model. Although the only way to really determine that is to train the model and to test the model using some data. Let's just put it broadly, right? Some data. We need to test the model and see what the error rate of the model is on that data. And what we did was we trained the model using our training set. We then tested the model using that same training set. And the decision tree regressor simply memorized the solutions for our training set when we trained the model and just map that to our when we were trying to predict the model, when we were trying to use the predict function to predict what the outputs would be. That obviously is not very advisable. And so instead we discussed how we need a different set essentially, a different not training set, but a test set when we are testing our model, when we're validating our model, and then use a different set when we're training our model. That way we know whether the model is truly doing well on unseen instances of the data. And so, because of that, this brings us to the conversation of cross validation. Cross validation involves splitting our training set, in our initial training set, into a training set as well as into a test set. And by splitting it into these two sectors, we're able to train our model using our training set and then test our model using a test set. This is one of the ways to do it. And in fact, we have a test set. We have a stratified test set that was stratified for median income. But another way that we can do this is a class that scikit-learn offers called the cross-validation scoring module, or the cross_val_score class. And what this class does is it splits the training set into some number of k-folds. And in using those folds, it's able to train the model on a certain number of those folds and test the model on one of those folds and perform this operations some k number of times. And so let's go through what exactly this process does. Okay, let me go ahead and rerun this here before we continue on. So let's go ahead and explain what exactly this is doing. And let's create a new cell here. All right, so what we're going to do is we're going to tell our model essentially, we want you to split our training set into some number of folds. Let's say we're going to split it into 10 folds. So we want to split training set into 10 folds. Okay? And then from there, what the model is going to do is it's going to train itself on 9 of those folds. In other words, k minus 1 of those folds. And test the model on one of those folds. Let's go ahead and label these folds, okay? Label folds, okay? We're going to label the folds as follows. A, B, or let me make this into Markdown just that way we can see this better here. We're going to label these folds. We're going to label them A, B, C, D, E, F, G, H, I, J, K. Okay, so you're seeing here that we have a total of 10. Of 10. So 10 now. Okay, so 10 of these folds. Okay, so using these 10 folds, now that they've been labeled, we're going to train our model using 9 of these folds, and we're going to test it using one of the folds. So what we're going to do is we're going to go through this process basically k times. I'll explain why we need to go through it k times. So in this case, k is equal to 10, so we're going to go through it 10 times. So each of these 10 times, each of the iterations is called an iteration. So let's go through the iteration. So let's go through the first iteration, just that we can kind of understand what exactly we're doing here. So our first iteration, we're going to have the training set, and we're going to have a test set. Okay? Like such. So our training set is going to be 9 of those folds. So in this case, we'll say 9, so we'll just take the first 9. Okay? And the test set is going to be one of those. Well, remember, it has to be one of those folds that we have not trained yet. So it's going to be j, right? We take the first 9, and then we're going to take the one that we haven't trained yet, which is going to be 9. And then from this, we're going to be able to create we're going to test the model using this particular training set and test set. And we're going to be able to get something called a mean squared error. Or in our case, it's going to be a negative mean squared error. And we'll explain why it's going to be a negative mean squared error later on. Okay, so we're going to get a negative mean squared error. From there, we're going to move on to our second iteration. In our second iteration, we're going to get a training set and we're going to get a test set as well. But in this case, our test set is going to be different from our previous test set. So our test set is instead going to be I. And our training set will be A, B, C, D, E, F, G, J. Okay? J was previously a part of our test set, but now it's being transferred over to our training set. So that's the way this process is working. Okay? So we're using the training set and then we're going to the test set. Okay? So the folds are the same in every single iteration. So just keep that in mind, okay? And so because of that, we can just move on to I. Right now, it's not necessarily going to be exactly the last one is going to become the test set, but I'm just doing that just because it's easier, to take the last one, push it in, take the next one, push it out, okay? It's kind of easier for me to think about it. But just generally speaking, we're going to go through this. We'll say dot, 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 right? We'll say dot, 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 and then we're going to go to our 10th iteration, okay? So you see that there. So we go through each of those individual iterations as such. All right. From there, what we'll do there is I want to talk about negative mean squared error. So let me include that as well, negative mean squared error, right? So for every single iteration, we're going to calculate what our mean squared error is. First of all, let's talk about the mean squared error. Remember what our mean squared error equation was. It's this equation. And this equation, again, it might look a little bit complicated, but it really isn't that complicated. All that we're doing is we're basically saying, what is our model producing as the output versus what should the model be producing, right? That's what we're really asking ourselves. And what the model should be producing, those are our labels. And what the model is producing, that's what the model is outputting. Okay, so we're grabbing those two values. Let's say the model should be producing 10, but the model produces 9. Well, what's the error if we subtract those two values? Well, the value will be 1, right? And then what we're going to go to is we're going to square that value. Why are we squaring it? Well, because we want to get rid of negative numbers, right? If the model is overfitting or underfitting, then it might be producing negative errors or positive errors, right? 10 minus 9 or 9 minus 10, depending on which one is the model and which one is what the model is actually outputting versus what the label should be. And so in order to alleviate that, we simply square it in order to get rid of the negatives. From there, we divide it by the number of instances, the number of instances in our training set. So the number of times we're going through this process that you see right over there. That's our mean squared error. Very simple, right? We're just taking the mean of the errors squared. That's really all we're doing. We're taking the means of the error squared. And that's why we have 1 over n, right? N instances. So that's what we're basically doing there. Now, what's this negative mean squared error that we're talking about here? Well, when we're using the cross_val_score class in scikit-learn, we are going to apply a negative scoring mechanism. And the reason for this is, I'm going to kind of try to keep it short a little bit, because one time I was explaining this and it went on for quite some time. But basically, think about how the error system works. The error system works now is if the error gets bigger, right? What does that mean? That means the model is doing worse, right? So if the model is producing an error, let's say we test one model and the model is producing an error of 70. And the other model is producing an error of 60 on the same training set. Which model is worse? Well, the model that's producing an error of 70, right? But intuitively, that makes sense, right? As the error rate goes up, the model is doing worse, right? In essence, if you will. But the negative mean squared error, basically what it does is it basically multiplies that mean squared error by a negative number, right? And so let's say that 70 flips over, right? Think about a number line, for example. A number line, it flips over from 70 to negative 70. The 60 flips over from 60 to negative 60, right? Just think about it's basically a mirror image of each other, right? It's kind of like if you've ever seen like a standard normal distribution, right? If you've seen a standard normal distribution, you know that that's going to be each side is going to be a mirror image of the opposite side, right? So think about it like that. So 60 becomes negative 60, 40 becomes 70 becomes negative 70. Well, in that case, negative 70 and negative 60, we just multiplied by a negative 1. Which one is worse? Well, obviously the negative 70, right? We just multiply by a negative 1. If we go back from negative 70 to 70, right, that's going to be 70, which means it's going to have a higher error rate. All we've done is we flipped the number around. So negative 70 is still going to be the worst. The model's going to be performing worse. And under negative 70 is going to be worse. Negative 60 is going to be a little bit better, right? But think about these two scenarios, right? In the original scenario where we're just calculating the mean squared error, the higher the mean squared error, the worse the model. In the other situation where we have negative 70 and negative 60, the higher the mean squared error, the worse the model is doing, right? Because negative 70 is less than negative 60. So in that situation, the higher the number, when we have negative mean squared error, the better the model is doing. So it's kind of just a different way of thinking about it. So instead of thinking about it as the higher the number, the better the worse the model is doing, the higher the error. Now we're thinking, now that with negative mean squared error, the higher the number, the better the model is doing. And it is kind of a little bit more intuitive. It depends. It depends how you think about it intuitively. But using your own intuition, typically speaking, when you think of higher numbers, right? Higher numbers are better and lower numbers are worse, right? That's typically speaking what you're doing, what you're thinking in your mind, right? And so if we're thinking about it from a negative mean squared error, it kind of makes sense a little bit since, like, for example, let's say you're evaluating, let's say, person A and person B. And let's just say hypothetically, the person A is a model, person B is a model. And we wanted to test them doing some task. Like let's say bowling or something, right? We have a model A, and model B. Well, the higher their scores, the better it would be, right? And so by using the negative mean squared error, we're able to say, okay, the higher their negative mean squared error, the better they're doing. The lower the mean squared error, the lower they're doing. Because humans, typically speaking, tend to associate higher values with better results and lower values with worse results. Now, really, I mean, I don't really understand why they're doing this because for me, if I look at a negative number, I could easily just flip it or like it's not really that difficult, right? A mean squared error makes much more sense. But regardless, that's what their ideology is. I think this just makes it more complicated. But regardless, I mean, you could just maybe memorize it, but maybe understanding it could be helpful for you. Okay, I don't really understand why they're doing it though. But regardless, they're doing it, and that's their reasoning for it. Okay, but if you don't understand the reasoning, you can just follow what they're doing. So, that's one of the reasons why they're using a scoring system known as negative mean squared error. Okay, so negative mean squared error is what they're using as their scoring system. Now, notice that when you take the square root, since our values are negative, you can't take the square root. Remember, for the root mean squared error, you can't take the square root of a negative number. And so because of that, you're going to multiply it back to a negative, which again, I feel like it kind of underrides the point again, because if you're multiplying it by a negative, then the true means, the root mean squared error is going to be back to the system that we had before, right? You know what I'm saying, right? It's going to be back to higher numbers worse, lower numbers better, right? Yeah, higher numbers worse, lower numbers better. So you're going to go back to the system that you already had. So I don't really understand why they're using a negative scoring system. I couldn't understand why they're doing it in the initial step, although then you're going back to what you already did before. So you can just try to understand that there. Okay, so cross validation score. So cross validation score, we already described all the theory behind it. Now that we've described all the theory, let's go and talk about the code a little bit. The code should be fairly simple for you to understand now that you've gone through all this. It's gonna remember what cross validation is doing. Cross validation is not training a model. This is very important. People try to get these two things confused. Cross validation is not training a model. Training a model is calling the fit function in scikit-learn. Calling the fit function is training a model. The step right over here, this one line right over here, this is what we're doing when we're training the model. When we're training a model, we're changing the model parameters and the model is determining a linear equation or a nonlinear relationship between the data or something like that. But when we are using the cross validation score class, I'm not going to call it cross val score class. I'll just call it cross validation score class, or we can call it CSV, CVS, right? CVS, we can call it like that. So when we use this CVS class, in other words, cross validation score class, we are not actually training the model. What we're doing is we are taking a model that has already been trained on. In this case, our tree regression, right? Our decision tree regressor. This is the model that we have right over here, and we are asking the cross validation score class in order to basically test the model on different inputs and outputs, and to go through the process that we described over here by splitting the prepared data and the housing labels into 10 folds, and then training and going through each of the iterations, calculating the negative mean squared error. That was our scoring system, right? And we're going to do that 10 times. And this is the reason why, because we're going to set the CV parameter equal to 10. Okay? So hopefully this all makes sense to you, right? Again, we're not really training the model. We're just sending the inputs and the outputs. We're sending our model, and we're saying what's the error rate for each of them. Okay, it's literally just that. This is literally just a mathematical calculation. That's all it's doing. It's literally just performing a mathematical calculation for us, and it's allowing us to depend on it doing the mathematical calculation while we still understand what the mathematical calculation is, rather than us programming the mathematical calculation. That being said, you still should understand some basic components of what the model is doing. Okay, so from there, what we're going to go and do is we're going to multiply that score. So we're going to get scores. And by the way, how many scores are we going to get? We're going to get 10 scores. So for each iteration, we're going to get a score. So keep that in mind. We're going to get a score for each individual iteration. So the score is equal to the number of scores is going to be equal to the CV parameter, okay? Which in this case is 10. Now it's going to be equal to a negative number, as we would expect, right? And then from there, we're going to multiply that negative number by a negative. And the reason for that is, again, we're calling the square root function. We can't take the square root of a negative number. Then we're going to get into imaginary numbers, and we don't want to work with imaginary numbers. So we're going to multiply that negative number with a negative in order to go back to a positive number, and then we're going to take the square root, which again, why are we using negative mean squared error if we're just going to go back to a negative number? I don't really understand that. But anyways, that's the system. Okay, so like I don't really understand that. Like, why couldn't we have just not skipped this step and then just done that, right? So again, you have to do that. Okay, so you can just accept it for what it is, and you can try to understand my explanation that I gave for it, at least their explanation for why you use it. Okay, so there you go. So what this is going to do is going to give us the root mean squared error. Why are we doing the root mean squared error? Well, remember again, we want to have the final answer in the units that the data is given in, that the training set and the labels are giving it or are given it. So that's why we're going to take the root mean squared, is because we want the data to be in the original data. We don't want it to be, for example, let's say the data was in this case it's dollars, right? Because we're calculating the median house price. Well, it's going to be dollars squared. We want to go back to dollars so we can understand it. That's why we're going to take the square root, right? Because we're squaring it here, we're going to do the inverse of squaring, which is taking the square root. Okay, let's go ahead and run this and see what we get. And again, remember, we're not training the model, we are testing the model. Okay, let me go ahead and print that out. Sorry, let me go ahead and print that out. All right. By the way, the code that we're writing for this is not very much, right? Coding is not very much important in machine learning. The main thing is understanding concepts, right? Concepts are way more important than even the coding, right? I mean, so coding is not that important, just 2 lines of code. So let's take a look at this. So we're seeing here, we should have 10 unique values, and it does take it out to several decimal places, actually. It's taking it out right now to 4, 5, 6, 7, 8 decimal places. That's quite a few decimal places there. And so you're seeing each of these values, and you can just read through each of these values and just kind of, gauge what this is. So you're seeing here roughly 70,000, 70,000, 64,000, 69,000, 67,000, seeing here 71,000, 67,000. All right, so you see here that this data is typically speaking or hovering around 70,000 or so, right? So is that a good mean squared root mean squared error? No, that's not a good root mean squared error. Now, if we want to actually do some actual, we can just program our own function that will do that. So we can just take a look at the data a little bit. So we can print out the scores, right? Obviously, we can take the mean of the scores by calling the mean function. And also we get the STD function. And what this does is it calculates the standard deviation. Okay, the standard deviation. So having the mean and the standard deviation is very useful because it'll calculate how spread apart our data is from that mean. Okay, and it's also very useful, especially if you have data that is follows a normal standard normal distribution. It is very useful to be able to have that. All right, let's go ahead and call this function, and we're going to pass in our scores, which in this case is going to be the tree root mean squared scores, and then we'll go ahead and print that out. Okay, or we don't have to print it out. We'll just call the function, and it'll print it out right over here. Okay, so this is a function that we programmed here that's just going to do that, just based some basic code. All right, so we see the values here. Mean is 69,027, which again hovers around 27. Standard deviation is 2,107. Okay, so 2,107 there. So you're seeing how those values line up there. All right, so is that a good error rate? No, well, that's not a good error rate whatsoever. Now, that being said, let's go ahead and try to see what's the error rate for our linear regression model, also using cross-validation, okay? And let's see which one has a higher error rate. And again, this is why it's useful, right? This is why this whole process is useful, because we can compare different models, right? We can compare different models. Keep in mind, by the way, that the folds are the same every single time you go through this. So fold A is the same fold A in the second iteration as in the third iteration, as in the fourth iteration, right? So it's always going to be the same fold. It's going to determine those folds. It is going to determine the folds. But keep in mind that these folds are going to be the same in every single iteration there. So again, this is just the same code. I don't think I have to explain that to you. Again, instead of using the tree regression model, we're going to use our linear regression model that we created right over here. And again, remember, we call it the fit function. This is the training step. This is the training step. And what we're doing right now is we're not training it. We're simply basically running a mathematical algorithm on it. We're going to pass in the housing prepared data, housing labels data, scoring, CV. Basically, everything's the same there. Only difference is that we're passing a linear regression model instead. And then we're going to call the display scores function that's going to basically display all the scores. Okay, let's go ahead and run this. It's going to display the scores, display the mean, and display the standard deviation. Let's go ahead and run that. It might take some time. All right, got it done very fast there. Linear regression, by the way, is pretty fast. So you're seeing there all the data there. It seems to be similar, actually. It seems to be pretty similar. I looked at the data here, and it looks like it's very, very close. But what we're seeing here is that the mean is 69,020. Now remember, this is the error rate, okay? Is this the negative mean squared error rate, or is this the positive mean squared error rate, or the mean squared error rate in general? This is the mean squared, this is the, well, none of this is the mean squared error rate. It's the root mean squared error. Is this the negative root mean squared error, or is this the positive root mean squared error? Well, it's the positive root mean squared error, which means the higher the root mean squared error is, the worse the model is doing. So it's a very similar numbers here, but you can see here that the decision tree regressor had a higher mean root mean squared error than the linear regression model did, just by a tiny number, actually. If we actually take those two numbers there and subtract them up to 8 decimal places, we get the exact number. Let me go ahead and print and run that. All right, so we get the number here, 6.6 roughly. I'll just take it out to 1 decimal point. Okay, I don't want to say all the rest of it. 6.6. Okay, 6.6. By the way, this is $6.6. Okay, $6.6. So $6.66. Okay. Now keep in mind the houses on average are about 100,000 or so. So this is not really. This is like a statistically almost irrelevant number, right? Like $6.66. Each house is like worth almost like hundreds of thousands of dollars, right? So in reality, I would say both models are roughly doing the same job, roughly, right? The decision tree regressor technically is doing worse, right? But we would not expect that, right? We would have expected that the decision tree regressor was handling more complicated relationships, right? Considering that it supported nonlinear relationships as opposed to simply linear relationships. But as you can see here, it's actually supporting worse results here, worse results. Now, there's one caveat here, and that one caveat is the standard deviation for the linear regressor is a lot bigger actually than the standard deviation for the decision tree. So that is a caveat there that you might want to be aware of. The standard deviation is a little bit bigger, and so because of that, you have to consider that in as well. But roughly they're the same, which we would expect. It wouldn't be. We would expect decision tree would be much better. But that's a comparison there. What can we do from here? Well, we have to experiment with different models, obviously. The models that we're experimenting with are not very good. There are other, we can regularize the model a little bit more by reducing the number of attributes increasing. We can do some manipulations there on the attributes, decrease the attributes, regularize our model, different things like that. But in our next lesson, we'll discuss how we can use a random. I think we're going to get into random forest a little bit. Going into random forest. Random forest is using several decision trees. It is very interesting as well, and we'll see how that'll all work out.